This is part 3 of a series of 3 videos on the integral of 1 over 1 plus tan x dx. And what I'm going to do here, since I covered the 2 methods I want to cover in the first 2, we actually want to change the problem. So I'm going to actually try to make this harder. Let's put in a 5 coefficient there. Let's just change these 1s to, let's say, a 3 and a 2. So now we've got a totally different problem. I think we've made the problem more difficult. So to start with, what I'm going to do, I'm going to multiply the numerator and denominator by cosine of x. And then that's going to give us 3 cos of x over 2 cos of x, this being distributed in. And then because tangent is sine x over cos x, when we multiply a cosine x, those are going to cancel. And we'll just be left with a 5 sine of x here. Now, what I would like to do, I like what we did in the previous videos, is we would like to have something with that's easier to work with. So we would like to have, let me write what we would like to have. We kind of wish this was something like 2 cos x plus 5 sine x over 2 cos x plus 5 sine x, right? Because then that's just 1, and we'd be able to integrate 1, which is easy. And then we would like this one to be, what is the derivative of this? So let's just pretend we're doing a u substitution. So if we have 2 cos x plus 5 sine x, and we get the derivative, see, the derivative of 2 cos x is going to be minus 2 sine x, and the derivative of 5 sine x is just going to be 5 cos x. So what I want this second integral to be is 5 cos x minus 2 sine x, right in our dx where we have space, over 2 cos x plus 5 sine x. Now the only problem with this is that's not remotely what we have here. We changed everything, right? We added cosines and subtracted sines, and we don't have that at all. Now, in the first video, we just kind of played with the sines and cosines to get it the way we wanted. But you'll notice here, like, how do I turn 3 cos x into 2 cos x and 5 cos x? In the first video, we used 1/2, but now we're getting into something where we'd be like, would I do over here? What would I do? 2/5? But then how would I get it to work with the sines? So basically what I'm saying is the trick that we used in the first video is either not gonna work or it's gonna be really hard. So what I'll do is use the method that we had in the second video. So basically, I think finding a way to manipulate 3 cosine x into what we have here is going to be difficult or impossible. Well, probably not impossible, but difficult. So we don't want to go down that road. What we'll do is what we did in this part 2 of this series is we created a coefficient and we said, okay, let's find out what that coefficient is going to be. So to do that, we know when we multiply this all out, we know it has to be 3 cos x. So let's just do that and try to solve for our a and b values, and then we have easy integrals to solve. So multiplying this, we'll have 2a cos x plus 5a sine x. Then we'll have a 5b cos x, and we'll have a minus 2b sine x, and that's going to equal 3 cos x. And then we can just create a system of equations. We can create 2 equations. We can separate our sines from cosines. We know we have these 2 cosine terms, so we know that 2a plus 5b is going to have to equal 3 cosines. And then we can do the same thing with sines. We have 5a sines here, and we have minus 2b. But on the right side of the equation, that's not an equal sign. But on the right side we have 0. We've got no signs here. So we just like write in a 0 sine x. So we can equate, we know that 5a minus 2b is going to have to equal 0. Then to solve this, I think what I'm going to do, I'll just work with this second equation. If we have 5a minus 2b equals 0, we can say that 5a equals 2b. And then we can solve for our a in terms of b. So a must be 2/5 b. Then we'll plug that back into the first equation. So we'll have 2 times 2/5 b plus 5b equals 3. Let's write 25b as 25/5 b. And this here is going to be 4/5 b. So adding those together, 4/5 and 25/5, we're going to have 29/5 b equals 3. Multiply 5 on both sides. Actually, you know, we'll multiply 5 29ths on both sides to make this a little quicker. Because that's going to cancel. And we find that b equals 15/29. Now we can go back, we have our equation for a, and we'll just plug this in here. So we can say, we have our value for b, so we can say a is just 2/5 times 15/29, but that's just going to be a equals 6/29. Now as you can see, I'm totally out of space, but what we'll do is we'll plug in this value for a and b here and here, and then we can solve our integral. Last part, we found these two coefficients for our integrals, 6/29 for our a value on the first integral and 15/29 for the second one. And so this is pretty interesting because we just created the integrals that we wanted to see basically, and then found the coefficients that that would correspond with that. So now what we have is we have kind of complicated coefficients, but the integrals are going to be really easy. So first, this piece here, this integral, because we have the same numerator and denominator, this is just 1. And the integral of 1 is going to be x. So that's pretty easy. And then in the second one, we already actually, the way we found this was we said this was u, and we said this was du by just taking the derivative. So we don't have to do that again. We know that we have du over u here. But that's a common integral, which is just ln of x, ln of absolute value of x. So we're going to have our 15/29, and this is going to be ln, I should have said ln of absolute value of u in this case. But then we're going to just substitute our u value back in. So for our final answer, we're going to have 6/29 x plus 15/29 ln of absolute value 2 cos x plus 5 sine x plus c, and we're done. So hopefully that demonstrates why we didn't want to, we like this method of getting easy integrals, but we don't have a good way to manipulate 3 cosine x into this form. So we use this kind of unknown coefficient method. And if you want to do more problems like this, I'll provide a link in the description. I have a quiz, Cramer's rule integrals. Cramer's rule refers to linear algebra, but as you saw, we can do it without linear algebra. We can just do it with regular algebra. So I'll provide a link in the description. Hope you check that out.